Okay, we move on to empirical relations for hydraulic conductivity. So this one is formulas to compute for hydraulic conductivity for if you cannot make use of the previous equations that was presented. So of course, empirical relations, this was based on tests that was conducted by certain individuals. So what if we're going to compute for hydraulic conductivity and the velocity, the parameters involved on constant head test and falling head test are not given, so you can still solve for those for the hydraulic conductivity or permeability coefficient using this hydraulic conductivity equations that was introduced by certain individual who conducted laboratory tests. So we have here Hazen formula. This is fairly uniform sense, so you can have the value for K using C times the d sub 10, of course, effective size for the 10%. This is the effective size, so the diameter of the 10% finer. So our C here is a constant that varies from 1 to 1.5. Then we have the Casagrande for fine to medium clean sand. K is equal to 1.4 E squared K sub 0.85. So our K here, of course, is the hydraulic conductivity at void ratio E, and our K sub 0.85 are equivalent to K at void ratio of 0.85. And we have the Kozeny-Karman equation. This is K is equal to C sub 1 K, multiplied to E cubed all over 1 plus E. So our K, of course, the hydraulic conductivity at a void ratio of E, and C sub 1 is a constant. Then Samarasenhe, Huang, and Drinevich, this is K is equal to C cubed E raised to N all over 1 plus E. Wherein our C sub 3 and N are constant to be determined experimentally. So those are empirical relations of hydraulic conductivity. So we move on now to equivalent hydraulic conductivity in stratified soil. It is being stated that in a stratified soil deposit where the hydraulic conductivity for flow in a given direction changes from layer to layer, an equivalent hydraulic conductivity can be computed to simplify calculations. So basically, why we have to compute for equivalent hydraulic conductivity? So it is in reality we have non-homogeneous soil, meaning to say we encounter different layers of soil. In one borehole, we have different layers with different properties. So if they have different properties, meaning to say they would have different, for every layer in one borehole, they could have different hydraulic conductivity or different hydraulic conductivity or permeability coefficient. So basically, we are after with a hydraulic conductivity for the whole entire borehole. So we have to compute, we have to resolve through equivalent hydraulic conductivity. So meaning to say, for example, you have a borehole from 0 to 5 meters depth, you have a different hydraulic conductivity. From 5 meters to 10 meters, you have a different hydraulic conductivity. From 10 meters to 15 meters, you have a different hydraulic conductivity. That is only in one borehole, but you have different hydraulic conductivity for a certain depth. So meaning to say, we are after, for example, you are after for hydraulic conductivity from 0 to 15 meters. So since for every 5 meters they have different hydraulic conductivity, and you wanted to get the hydraulic conductivity from 0 to 15 meters, so you can get the hydraulic conductivity for that by computing the equivalent hydraulic conductivity. So this is an illustration for equivalent hydraulic conductivity in stratified soil. So this is a, we have here Z sub 1, Z sub 2, Z sub 3, referring to the depth for every layer. And for every layer, you have K sub 1, K sub 2, and K sub 3. And of course, the total of this is H, that is the total height of the all of the layers. So for equivalent hydraulic conductivity in stratified soil, there can be a parallel flow which is along x direction, and there can be a normal flow which is along y direction. So how are we going to compute for the hydraulic conductivity if you have a parallel flow and you have a normal flow. So you're going to resolve that one through these equations. So to compute for equivalent hydraulic conductivity in the x direction, which has a parallel flow, you're going to have this one. So k sub x equivalent, so this is now our equivalent hydraulic conductivity that you're going to solve, times h, the total height of the soil layer, is equal to the summation of k of x times z. So meaning to say, you're going to add all of the hydraulic conductivity multiplied to the depth per layer. So it can be you can have k sub x1, z sub x1 plus k sub x2, z sub x2, and so on. So this is hydraulic conductivity for every layer times the height of that particular layer. Then you try to simplify this one, divide by h, you can compute now for the equivalent hydraulic conductivity. So similarly, if you're going to compute for the equivalent permeability, or the equivalent permeability in the z direction, or that is the normal flow, so you're going to have this equation, h all over k sub z equivalent is equal to the summation of z all over k sub z. So basically for this, you simply have to simplify so that you can get the equivalent hydraulic conductivity, k sub z equivalent. So that is for a normal flow. So if you're going to have a sample problem, the figure shows layers of soil in a tube that is 100 mm by 100 mm in cross section. Water is supplied to maintain a constant head difference of 400 mm across the sample. The hydraulic conductivities of the soil in the direction of flow through as follows. So you have here a soil and with corresponding hydraulic conductivity and of course the porosity. You're going to calculate the equivalent K in centimeter per second, calculate the rate of water supply in cubic centimeter per hour, and calculate the seepage velocity through soil C in meter per second. So for this one, this is the illustration, this is the figure for our problem. So if you're going to observe, you have an inflow of water. It will passes through soil A, soil B, and soil C, and it has an outflow. So the head from the surface of the from the water surface of the inlet towards the surface of the outlet, that is of course our constant head difference. So that is equal to 400 mm, and we are given with the length per soil layer, which is 150, 150, and 200. So this problem is a normal flow. So basically, we're going to use the equation for the normal flow to compute for the equivalent hydraulic conductivity. So this is our equation. So you simply have to substitute our HO, our total head, total length of the soil sample. Then you simply have to substitute the length of the soil sample, the length of each of the soil sample in the hydraulic conductivity of each soil sample. So you simply have to substitute all of those and you simplify. So you get 0.001057 centimeter per second. So this is the equivalent hydraulic conductivity for this particular setup of a soil sample. Then the second one is to determine the flow rate. So flow rate is Q is equal to Ki times A. Basically, we have to compute our I, which is H all over L, and we have to identify our H, which is given as the constant head difference, which is 400 all over the length, total length of the soil sample 500, so that gives us 0.80. So therefore, if you try to substitute all of those, Q now is equal to 0.08456 cubic centimeter per second, or that can be equivalent to 304.4 cubic centimeter per second. And the last one is to compute for the seepage velocity through soil C. So to compute for the seepage velocity, we are going to obtain first the average velocity, or the velocity discharge, using the equation Q all over A. So we're given with our Q, we have computed that one, we divide that with the area of the soil sample. So, and you try to simplify, it gives us 0.08456 meter per second. And since we have this value now, the discharge velocity, for the average velocity. You can compute now for the seepage velocity through soil seep. So that would be average velocity all over n. The porosity for soil seep is 0.22, and you get the value of 0.384 meter per second. Now we move on to flow through layers of aquifers. So aquifer, of course, when we talk about aquifer, that is an underground layer of permeable rock, sediment, or soil that yields water. So that is an aquifer. So we have here layers of aquifers. So how are we going to compute for our Q, which is our flow per unit width? So for this one, so this is the formula for this particular figure, aquifer in horizontal layer. So you're going to have here the formula to compute for the equivalent hydraulic conductivity. And to compute for Q, our flow per unit width, that is K equivalent times I times A. So basically, we have to identify our I. Our I here is d sub 1 minus d sub 2 over L. This is the water surface towards the bottom of the impervious layer, that is D1. This one is the water surface on this, which is in lower compared to D1, so this is our d sub 2. So D1 minus D2 over L, that is our I, and you can have your area A, which is equivalent to, this is the area, D1 plus D2 over 2 times 1, because we're considering per unit width. So basically, if you have this, simply have to substitute to this equation, you can get now the value for flow per unit width. And if you have an impervious layer for non-homogeneous unconfined aquifers, for this one, you have a normal flow. So basically, for a normal flow, you have this equation to compute for the equivalent hydraulic conductivity. And still, we are after with the flow per unit width, Q. You have K equivalent, whatever is the value that you have computed for the equivalent hydraulic conductivity. Multiply that one to I, our hydraulic gradient, times the area of this unconfined aquifer. So our I is D1 minus D2 over L. L, of course, is the length of our, total length of our aquifer. So for this one, you have A, which is the area, so of our soil layer. So that would be D1 plus D2 over 2 times 1, because we are considering a unit width. So that is basically for this setup, for this illustration for non-homogeneous and confined aquifer. So we have here a sample problem. A confined aquifer underlies an unconfined aquifer as shown in this figure. We are given with D1, D2, H1, H2, K sub 1, K sub 2, and L. We are going to compute for equivalent hydraulic coefficient of permeability in horizontal direction, calculate hydraulic gradient, calculate the flow of water from one stream to another per meter width. So for that one, we simply have to compute first, this is our illustration. So we have to compute first for our equivalent hydraulic conductivity. This is a parallel flow, so use the equation for the parallel flow, substitute our H, total length of the soil sample, then K equivalent per layer times the height per layer, so that is 31.615 meter per day. The second one, hydraulic gradient, basically that would be H, which is this one, from the surface of D1 to the surface of D2, which is 18, all over the length of the soil sample, which is 2000, that is 0.009. And the last one, the discharge K equivalent I times A. So we have computed our K equivalent. Then our area would be H average times 1, because we're considering 1 per unit width. So that would be equivalent to 59 plus 41 divided by 2. So D1 plus D2 divided times 2 times 1. That is 50 meter per second. We substitute this area times the I we have computed and times equivalent hydraulic conductivity. You get now your Q, which is 14.227 cubic meter per day.